All right, our experiments with the six-pack Ranger Smack has inspired me to move on to the next level of hydroxy production. So far, we've been using six individual cells to try to magnify the output capacity of the generator unit. It's entailed a lot of diagnostic and maintenance issues, lots of leaks. It's hard wiring up six of these units and getting them to perform consistently over duration of test runs. So I've taken an idea that I've been working on for the past couple of years, and I've decided to step it up and come up with a more integral design, which features a higher output for less current and less heating. Basically, the issue is this. Most people, when they first learn about hydroxy production, one of your first tests is going to be you're going to take a couple of plates like this, and you're going to hook a battery across the two plates. You're going to put it in a vat of water, and you're going to make some hydroxy gas while cool neat. And then as you further your studies and you research more into the properties of electrolysis and hydrogen production, you realize that, well, most of our batteries are 12 volts. So if you put 12 volts across two stainless steel plates, one of the first things you learn is about 1.24 volts of that power is going into making gas, and the remainder of the voltage, that extra 10 volts there, is used to make heat. So the next challenge for you researchers out there is to lower the voltage to reduce the heat, while simultaneously being able to put enough current to the cell to get appreciable gas output. And those kind of parameters what led to my design of the step gap incorporated into the smack booster. But now I'm looking for more. And so to date, the most efficient cell for its size, this is a Bob Boyce design. It's called a Taro cell, but Bob Boyce is responsible for designing this cell. And basically, its design was to address the heating issue caused by overvoltage between cell plates. So basically what you have is seven separate isolated cells applied with a 12 volt across to give you basically 2 volts per cell, which minimizes your cell heating. It enables you to run cooler, prevents you from boiling the water. Now the inherent problem with this type of cell is that you have to isolate each container. Each of these individual cells has to be isolated physically, sealed off from each other to prevent current from jumping across. Current doesn't want to go through the cells. It just wants to go from one end to the other. It doesn't want to have to do work in between each individual cell to create the gas, because it takes power to make that gas. So the current would rather just jump around the whole edge of the thing and just end up producing gas on the plus and minus terminals. And that inspired the step gap design, because separating the plates reduces the amount of jumping current between each cell. But still, this doesn't offer a lot of surface area. To get a large surface area, you've got to really make a huge, gigantic unit that isn't practical to fit in most vehicles. So there's limits to what you can do with this kind of design. Not to mention that it's kind of difficult to construct, and it's very difficult to maintain the water level within each of these individually sealed cells. You kind of have to, you got to pipe water into each one of them at equal amounts. Otherwise, the levels start to vary. It's a very difficult cell to maintain over a long period of time. But this cell here is basically comes off of the same thought process of the Bob Boyce 101 plate cell design, where you put 155 peak-to-peak volts DC across the cell stack, and basically you get about 1.8, 1.9 volts across each cell. Each cell is isolated. It runs cooler because you've only got 2 volts applied. Okay, but again, you have a construction issue. There's a lot that goes into the construction of this box. You have to mill a bunch of slots. Each plate is an individual cell, all on its own, sealed off. Maintaining the level, especially when you're only 2-3 millimeters apart between each of these plates. Each one has to be filled individually. It leads to a logistical plumbing nightmare. So still, very efficient, but difficult to maintain, difficult and expensive to build. Okay, so the idea here is if you can make 6 separate containers, okay, each individually, it's easier to monitor. Say you have a cell like we just showed over here, where say you had 2 plates in a cell like this, and you had 6 of them all lined up in a row in series. You would see 2 volts across each one of these with a 12-volt applied. Okay, so I took this idea of compartmentalizing each cell, kind of like what the taro cell does, except making it a little easier to maintain as far as fluid level goes. This bath can be of any size, okay, so it's a little bit easier to fill and maintain. All right, but still having 6 individual containers is kind of a pain in the butt. But it goes along the line of splitting the voltage without having to use electronics into a lower voltage of about 2 volts to reduce your heating. Okay, so then, I'm not sure who came up with this first, this idea of having a Boyce-style kind of a box partitioned into 6 or 7 separate containers. I think this is 1, 2, 3, 4, 5, 6, 7. 7 because most alternators pump out 13.8 volts DC. So if you separate it into 7 containers, that's just under 2 volts. I saw this drawing from Patrick Kelly. He actually sent it to me in attachment. Right about the same time, I was having the exact same idea about trying to separate containers in one box into 7 more or 6. I actually wanted to do 6 because I was thinking of 12-volt applied, not 13.8. So I was kind of trying to come up with an idea of incorporating one box with 6 or 7 different compartments with cells in each compartment. And he sent me along this diagram, and that really kind of solidified my thought about getting 2 volts without having to use special electronics. Okay, so basically what I've done some studying. This is the Frank Roberts design, okay? And Frank inspired me in several different ways. A lot of his design characteristics were responsible for the development of the smack booster, including the step gap. You see these gaps between each? These are cell stack. These are parallel plate, 20-plate cell stacks. There's 3 of them. So basically, if you apply 12 volts across the whole stack, it's divided into 3 voltage potentials. So you get 4 volts per 20 cell stack. Okay, so each single plate sees a 4-volt differential. And the reason for the spacing is it's kind of like the trying to take advantage of the Bob Boyce isolation protocol, where if you increase the distance between the separate cell stacks, it's harder for the current to jump across that electrolyte, because as you increase the distance, the resistance of the electrolyte also increases, and it wants to go through this rod right here rather than across the electrolyte. Okay, so Frank Roberts was on the right track as far as trying to use distance in the electrolyte to segregate the cell stacks, and this is what led to my step gap design. This distance here is what inspired me to take each individual cell and separate them out. As you're all familiar with now, the step gap design basically takes a cell plate and spaces it apart, and then makes another cell plate and spaces it apart, and this space reduces the current loss by increasing the potential between the plates.